Hello, everyone. In this video, we will study sequences, or infinite sequences, including the limit of sequences, properties of limits of sequences, monotonic sequences, bounded sequences, and the monotonic sequence theorem. Sequences. An infinite sequence is a list of numbers in a definite order. Each number is called a term. The first number is the first term, the second number is the second term, the third number is the third term, and in general, the nth number is the nth term, and so on. A sequence can be written succinctly as a n from n equals 1 to positive infinity, or just in terms of its general term, a n. The general term of a sequence is the formula for the nth term of the sequence. That is, a n is f of n, where each term depends on a positive integer n. Thus, we can thought of a sequence as a function whose domain is the set of positive integers. The graph of a sequence is the graph of the equation y equals f of n, where n is 1, 2, 3, and so on. And f of n is the formula for the general term, a n. The graph is composed of points with location along the horizontal determined by positive integers n, and location along the vertical determined by the value of the term, a n. If y equals f of x, and a n is equal to f of n, then the terms of the sequence are sample values of f at x equals n. It means that the terms of a sequence are the sample values of a function if they correspond to the values of the function when the domain is the set of positive integers. Example: find the general term and plot the graph of the following sequence. Solution: figuring out the general term of a sequence comes down to recognizing a pattern in the sequence. For the given sequence, each term has a corresponding value of n. The denominator in each term is a power of 2. Then, we can rewrite the sequence in terms of power of 2. Notice that each n and the corresponding exponent differ in value by 1. As a consequence, each term of the sequence can be written in terms of n-1. Therefore, the general term of the sequence is equal to 1 over 2 raised to n-1. Because the general term equals 1 over 2 raised to n-1, where n is 1, 2, 3, and so on. Which consists of points with location along the horizontal determined by positive integers n, and location along the vertical determined by the value of the term. The terms of the sequence are sample values of the function f of x equals 1 over 2 raised to x minus 1 at x equals n. Limit of a sequence. Suppose we have a list of numbers If the terms of the sequence, an, approach L as n becomes sufficiently large, then the sequence has the limit L. That is, the limit of an, as n approaches positive infinity, is equal to L. The limit of a sequence can be illustrated using the following graph. As n approaches positive infinity, the terms of the sequence approach the limit. Now, suppose there is a function f on the interval 1, positive infinity. If the limit of f of x, as x approaches positive infinity, is equal to L, and each term is a sample value of f at x equals n, then, the limit of an, as n approaches positive infinity, is equal to L. It means that if the terms of the sequence are taken from a function that has a limit L at infinity, then the sequence also has the limit L. Depending on the existence of the limit, the sequence converges to L if the limit exists. This means the sequence is convergent. Meanwhile, the sequence diverges if the limit does not exist. This means the sequence is divergent. In order to calculate the limit of a sequence, we need to apply some techniques in computing limits such as properties of infinite limits, sum or difference, product, and quotient properties. For sum or difference and quotient rule, if the limit of one sequence is infinite and the limit of another sequence is a finite number, then the limit of the sum or difference of these sequences is also infinite, whose sign depends on the sign of the infinite limit. While the limit of the quotient of the finite limit and the infinite limit is equal to 0. Now for the product rule, if the limit of one sequence is infinite and the limit of another sequence is a finite number but not 0, then the limit of the product of these sequences is also infinite. It is positive infinity if the sign of the limits of the sequences are the same, or negative infinity if the sign of the limits of the sequences are different. Simplify or rewrite. Use identities, factoring, dividing out common factors, and rationalizing to simplify or rewrite the limit of an algebraic or transcendental function. Limits at infinity. Use limit at infinity expressions, such as the limit of a reciprocal, the limit of a polynomial, the limit of a transcendental function, to evaluate the limit. Change of variables. Apply this technique for composite functions. The inner function is replaced by a new variable, and the limit is taken with respect to that new variable. And L'Hopital's rule. This method is for limits leading to indeterminate forms. If the initial evaluation of the limit of a quotient is infinity over infinity or 0 over 0, take the limit of the quotient of the derivative of the numerator and the derivative of the denominator. Example. Find the limit of the following sequences. A list of numbers. B A sequence of sample values of a rational function. C. A sequence of sample values of a composite function. Solution. A. For the first sequence, we found out that its general term is equal to 1 over 2 raised to n-1. We can tell its limit by looking at its graph. However, we can also find the limit analytically by change of variables. Let m equals n-1. As n approaches positive infinity, n-1 also approaches positive infinity. Thus m approaches positive infinity as well. Use a limit at infinity expression of an exponential function. Therefore, the limit of the sequence is equal to 0. In other words, the sequence converges to 0. B. The sequence of sample values of a rational function. First, find the limit of the given function. Use properties of infinite limits and a limit at infinity expression. Because the initial evaluation of the limit leads to infinity over infinity. Rewrite the rational function by dividing the numerator and the denominator by the highest power of x. Use the following limit at infinity expression. The limit at positive infinity of the rational function is 3. Therefore, the limit of the sequence is equal to 3. Because the initial evaluation of the limit leads to infinity over infinity. Another solution to this problem is to use L'Hopital's rule. Rewrite the rational function by differentiating the numerator and the denominator. Use properties of infinite limits and a limit at infinity expression. Which leads again to infinity over infinity. Differentiate the numerator and the denominator again. The limit at positive infinity of the rational function is 3. Therefore, the limit of the sequence is equal to 3. That is, the sequence converges to 3. C. The sequence of sample values of a composite function. First, find the limit of the given function. Use change of variables. Let y equals x squared minus 3x plus 9. As x approaches positive infinity, the quadratic polynomial approaches positive infinity. Hence y approaches positive infinity too. Use the following limit at infinity expression of the natural logarithm function. The limit at positive infinity of the composite function is positive infinity. Therefore, the limit of the sequence is positive infinity. That is, the sequence diverges to positive infinity. Properties of limits of sequences. Suppose two sequences are convergent and k is a constant. The following properties hold. Scalar multiple. The limit of a constant multiple of a sequence is equal to the constant times the limit of the sequence. Sum or difference. The limit of a sum or difference of two sequences is equal to the sum or difference of the limits of each sequence. Product. The limit of the product of two sequences is equal to the product of the limits of each sequence. Quotient. The limit of the quotient of two sequences is equal to the quotient of the limits of each sequence, provided the limit of the denominator is not zero. Power. The limit of a power of a sequence is equal to the power of the limit of the sequence. Where p is a number greater than 0, and an is greater than 0. Example 1. Suppose there are two sequences A and B. Find the limit of these sequences. A. Sequence C with the following general term. B. Sequence A times sequence B. C. Sequence C divided by sequence B. Solution. A. Substitute the general term of sequence A. Apply properties of limits of sequences. Use a limit at infinity expression of an exponential function. Hence, the limit of the sequence is equal to 2. It means that the sequence converges to 2. B. Substitute the general terms of sequences A and B. Apply a property of limits of sequences. Using limits at infinity expression of an exponential function. The limit leads to an indeterminate form. We can try L'Hopital's rule, or we can rewrite the function by combining the exponential functions. Use a limit at infinity expression. Thus, the limit of the sequence is equal to 0. That is, the sequence converges to 0. C. Substitute the general terms of sequences C and B. Apply a property of limits of sequences. For the numerator, use the computed limit for sequence C. For the denominator, apply a limit at infinity expression of an exponential function. Then, use the quotient rule of infinite limits, where the limit of the numerator is a finite number and the limit of the denominator is an infinite number. Therefore, the limit of the sequence is equal to 0. It means that the sequence converges to 0. Example 2. Suppose there are three sequences A, B, and C. Find the limit of these sequences. A. Sequence B times sequence C. B. Sequence A divided by the product of sequence B and sequence C. C. The cube of 1 divided by sequence A. Solution. A. Substitute the general terms of sequences B and C. Apply a property of limits of sequences. Use a limit at infinity expression of an algebraic function. The product of two positive infinities is also positive infinity. Thus, the limit of the sequence is positive infinity. That is, the sequence diverges to positive infinity. B. Substitute the general terms of sequences A, B, and C. If we apply properties of limits of sequences, the result is the indeterminate form infinity over infinity. Use L'Hopital's rule. Differentiate the numerator and the denominator. Apply the quotient rule. The limit of the numerator is a finite number, while the limit of the denominator is an infinite number. Using the quotient property of infinite limits, the limit of the sequence is equal to 0. It means that the sequence converges to 0. C. Substitute the general term of sequence A. Apply the power property of limits of sequences. Apply the quotient rule. Use the quotient rule of infinite limits, where the limit of the numerator is a finite number and the limit of the denominator is an infinite number. Hence, the limit of the sequence is equal to 0. That is, the sequence converges to 0. Squeeze theorem for sequences. Suppose there are three sequences. If the terms of one sequence is always bounded below and above by the other two sequences, for all n after a specific number, and the bounding sequences both converge to the same number L, then the squeezed sequence also converges to L. Example. Evaluate. The limit of e raised to negative n times the cosine of pi n, as n approaches positive infinity. Solution. The cosine function has values ranging from -1 to 1. Thus, the cosine of pi n is bounded below by -1 and bounded above by 1. Multiply the inequality by e raised to -n in order to arrive at the given sequence. Take the limit of the lower and upper sequences. Use a limit at infinity expression of an exponential function. The limits are both equal to 0. Because the given sequence satisfies the inequality, and the limits of the lower and upper sequences are equal, the limit of the given sequence is also equal to 0. It means that the sequence converges to 0. Absolute value theorem. Consider a sequence with negative and positive terms, and the sequence of its absolute values. If the sequence of absolute values converges to 0, then the sequence also converges to 0. Evaluate the limit of e raised to negative n times the cosine of pi n, as n approaches positive infinity. Solution. Recall that the cosine of pi, cosine of 3 pi, cosine of 5 pi, and so on is equal to -1, while the cosine of 2 pi, cosine of 4 pi, cosine of 6 pi, and so on is equal to 1. The values of the cosine function at multiples of pi alternate between -1 for positive odd integers and +1 for positive even integers. Consequently, the cosine of pi n can be written as -1 raised to n, which is equal to -1 if n is odd and +1 if n is even. Take the limit of the absolute value of the given sequence, and substitute the new expression for cosine. The absolute value of -1 raised to n is +1. Meanwhile, the function e raised to -n is always positive for any value of n. It follows that the absolute value of the sequence can be now written as follows. Use a limit at infinity expression of an exponential function. It follows that the limit of the absolute value of the sequence is equal to 0. Thus, the limit of the sequence is equal to 0. It means that the sequence converges to 0. Composite function. Suppose a sequence converges to L, and f is a continuous function at L, then the limit of the function of the sequence is equal to the value of that function at the limit of the sequence. Example: if sequence A is given and f of x is the natural logarithm of x, find the limit of the natural logarithm of sequence A, as n approaches positive infinity. Solution. Find the limit of the given sequence by simplifying the general term. Use properties of limits of sequences and a limit at infinity expression of the reciprocal function. The limit of the given sequence is equal to e. The natural logarithm function is continuous on its domain, which includes x equals e. As a result, we can apply the composite function property. The limit of the natural logarithm of the given sequence is equal to the natural logarithm of the limit of the given sequence. Therefore, the limit of the function of the given sequence is equal to 1. That is, the sequence converges to 1. Exponential sequence. The sequence consisting of r raised to n converges if r is between -1 and 1. And the sequence converges to 0. Or if r is equal to 1. The sequence converges to 1. Meanwhile, the sequence consisting of r raised to n diverges for other values of r. The limit of the sequence does not exist. The graph of other divergent sequences, such as when r is -1, the terms alternate between -1 and +1. And when r is less than -1, the terms diverge to -infinity. Monotonic sequences. A sequence is increasing if for any term in the sequence, the next term is greater than or equal. An increasing sequence can be written as the following inequality. The equality means that an increasing sequence may have consecutive equal terms, as long as the terms before are lower and the terms after are higher. A sequence if decreasing if for any term in the sequence, the next term is less than or equal. A decreasing sequence can be written as the following inequality. The equality means that a decreasing sequence may have consecutive equal terms, as long as the terms before are higher and the terms after are lower. An increasing or decreasing sequence is called monotonic. Bounded sequences. Bounded above. A sequence is bounded above if there is a number m such that every term of the sequence is less than or equal to m, where m is an upper bound of the sequence. This monotonic sequence is bounded above by an upper bound m. Although its limit L is not necessarily equal to m, as the limit L may be less than or equal to an upper bound m. This sequence is also bounded above by m, although it is not monotonic. Meanwhile, a sequence has no upper bound if the limit of the sequence does not exist, and it is positive infinity. As an illustration, this sequence has no upper bound because it diverges to positive infinity. Bounded below. A sequence is bounded below if there is a number m such that m is less than or equal to every term of the sequence, where m is a lower bound of the sequence. This monotonic sequence is bounded below by a lower bound m. Although its limit L is not necessarily equal to m, as the limit L may be greater than or equal to a lower bound m. This sequence is also bounded below by m, although it is not monotonic. Meanwhile, a sequence has no lower bound if the limit of the sequence does not exist, and it is negative infinity. As an illustration, this sequence has no lower bound because it diverges to negative infinity. Bounded sequence. It is a sequence that is bounded above and bounded below, which means all the terms of the sequence are anywhere from a lower bound to an upper bound. In the first graph, the sequence is bounded and monotonic. it means that it is bounded below, bounded above, and increasing. Meanwhile, a sequence can also be bounded below, bounded above, and decreasing. In the second graph, the sequence is bounded but not monotonic. It means that it is bounded below, bounded above, but it is neither increasing nor decreasing. Monotonic sequence theorem. It states that if a sequence is bounded and monotonic, then it is convergent. In the first graph, the sequence is bounded below and bounded above. That is, the terms of the sequence do not go beyond its lower and upper bounds. It is also an increasing sequence. Hence, it is convergent. And its limit at positive infinity is less than or equal to an upper bound m. In the second graph, the sequence is bounded below and bounded above. That is, the terms of the sequence do not go beyond its lower and upper bounds. It is also a decreasing sequence. Thus, it is convergent. And its limit at positive infinity is greater than or equal to a lower bound m. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.